Far out beyond the orbit of Neptune, in the deep, cold darkness of the Kuiper Belt, spins a world that seems to defy the very laws that govern our solar system. It's not a perfect sphere like Earth or Mars, but a rapidly tumbling, football-shaped oddity known as Haumea. This isn't just another frozen rock in the void. It is a cosmic puzzle box, a dwarf planet that challenges everything we think we know about how planets form and behave. Its very existence is a question mark written across the stars, a place where the ordinary rules of physics appear to have been bent, broken, or rewritten entirely. For astronomers, Haumea represents one of the most profound and captivating mysteries waiting to be solved. A celestial body so strange that every new discovery seems to create two more questions in its wake. Today, we're embarking on a journey to this distant and enigmatic world to uncover its deepest secrets. We will be exploring 25 of the most baffling, head-scratching, and utterly fascinating mysteries that shroud Haumea. From its impossibly fast rotation that should have torn it apart, to its glittering family of icy moons and the strange, crystalline water ice that coats its surface, each clue we uncover only deepens the intrigue. What catastrophic event shaped this world? How does it possess a ring system, a feature more commonly associated with gas giants? And what hidden forces are at work in the frozen depths of the Kuiper Belt that could create such a bizarre object? This is more than just a list of facts. It is a detective story written across the cosmos, a journey into the unknown that speaks to our deepest human impulse to explore and understand the universe around us. As we count down these 25 unexplained mysteries, prepare to have your perception of our solar system challenged. We are about to dive into a realm of scientific anomalies and cosmic curiosities that continue to stump the brightest minds in astronomy. This is an invitation to look past the familiar planets and venture into the shadowy frontiers of our own cosmic backyard, where worlds like Haumea remind us that the universe is far stranger, more wonderful, and more mysterious than we could ever imagine. So, let's begin our descent into the unknown, starting with the very first clue that marks Haumea as a true outsider in our solar system. Our first mystery is literally the shape of the thing. When we picture planets, we think of spheres. Gravity pulls mass inward evenly, smoothing a world into a ball, just like it has for Earth, Mars, and even Pluto. Haumea, however, breaks this fundamental rule. It is not round. Instead, it has been stretched and flattened into a distinct ellipsoid, a shape often compared to a flattened rugby ball or a giant tumbling potato. This is our first and most visual clue that Haumea is a world governed by different rules. The cause of this bizarre shape lies in its absolutely dizzying rotational speed. Haumea completes a full spin on its axis in less than 4 Earth hours. To put that into perspective, while our planet takes a leisurely 24 hours for one day, Haumea experiences more than 6 full days in that same time. This rapid rotation generates immense centrifugal force, a powerful outward push that fights against the inward pull of gravity. At its equator, this force is so extreme that it has literally stretched the dwarf planet's surface outward, while gravity manages to keep its poles compressed. The result is a world that is significantly longer than it is wide, a cosmic oddity spinning with frantic energy in the silent dark. This characteristic immediately sets Haumea apart from every other known dwarf planet in our solar system. While others, like Eris and Makemake, are near-perfect spheres, Haumea's elongated form is a testament to a violent and energetic past. This brings us to the central question that hangs over this entire mystery. What could have possibly happened to set it spinning so catastrophically fast? A planet doesn't just naturally form with this kind of rotational velocity. The most widely accepted theory points to a colossal impact billions of years ago, a monumental collision with another large object that struck Haumea a glancing blow, transferring a tremendous amount of angular momentum and setting it off like a top. This single event wouldn't just explain the spin. It could be the key that unlocks many of the other mysteries we'll explore, from its family of moons to its unique composition. The shape of Haumea is not just a curious fact, it is the first piece of evidence in a cosmic crime scene, pointing directly to a violent, formative event that forever altered this distant world. Building directly on that violent impact theory, we plunge into our second great mystery. What was the precise origin of Haumea's hyperrotation? If its shape is the evidence, then the cause of its spin is the central crime we're trying to solve. The giant impact hypothesis is the prime suspect, a compelling narrative that fits many of the clues. Picture a younger, more chaotic solar system, with the Kuiper Belt a crowded shooting gallery of icy protoplanets. In this scene, a young Haumea, perhaps more spherical and sedate, suffers a catastrophic sideswipe from another massive object. This wasn't a direct head-on collision that would have pulverized both bodies, but a spectacular glancing blow. The physics of such an event are fascinating. It's like striking a billiard ball off-center, transferring a huge amount of angular momentum and sending it spinning wildly across the cosmic table. This single cataclysm could have done more than just set Haumea twirling. It might have blasted vast amounts of debris into space, debris that would later coalesce to form its moons, Hioka and Namoka, and even contribute to the family of smaller, icy bodies that share its orbit. Yet, as elegant as this theory is, it faces significant challenges. For one, computer simulations of such an impact struggle to recreate the precise conditions we see today. The collision would have had to be incredibly specific, powerful enough to impart this tremendous spin, but not so violent as to shatter Haumea completely. It also needs to explain the curious fact that Haumea is almost pure rock, covered by only a relatively thin shell of water ice. A giant impact would have generated so much heat that it should have melted and dissipated much of this ice, leaving us with a different surface composition than the one we observed. This forces scientists to consider alternative, more speculative ideas. Could Haumea's spin be the result of a long-lost gravitational dance? In its distant past, perhaps it traveled much closer to Neptune. A prolonged, complex tidal interaction with the giant planet could have, over eons, torqued and accelerated its rotation, similar to how Earth's gravity has locked the Moon into showing us only one face, but in a far more dynamic and speed-boosting way. After this gravitational slingshot effect did its work, Haumea could have then been flung back out to its current remote orbit, leaving only the spin as a relic of that ancient encounter. There are even more exotic possibilities. Some researchers point to a process known as rotational fission. Imagine an early Haumea spinning fast but not impossibly so, beginning to warm up from the decay of radioactive elements in its core. As it heats, it becomes more malleable, almost fluid. This could have caused it to deform and spin even faster, a positive feedback loop that ultimately led to it shedding material from its equator. Material that became its moons, which in turn allowed the dwarf planet to settle into its current frantic rotation rate. Proving any one of these theories is the real hurdle. We are dealing with an event that likely occurred over 4 billion years ago, with all the direct evidence long since settled or scattered across the solar system. Our clues are circumstantial: the spin itself, the family of orbiting objects, the surface composition. Each new observation from powerful telescopes adds a piece to the puzzle, but the full picture of how Haumea became the solar system's fastest spinning dwarf planet remains frustratingly out of focus, a shadowy event from the dawn of our planetary system that continues to challenge our understanding of celestial mechanics. Just when we thought Haumea couldn't get any stranger, astronomers made a discovery that sent shockwaves through the field of planetary science. This bizarre, football-shaped dwarf planet, already an outlier in every way, was found to possess something utterly unexpected: a ring. We typically associate rings with majestic gas giants like Saturn, vast worlds with immense gravity capable of sculpting and holding onto these delicate structures. The idea that a small, rocky, and frantically spinning object like Haumea could maintain such a feature seemed to defy all conventional wisdom. This revelation didn't just add another oddity to the list, it fundamentally challenged our understanding of where rings can form and what physical processes are required to sustain them. The ring's discovery was a masterclass in patient, precise astronomy, relying on a technique called a stellar occultation. On January 21, 2017, astronomers knew that Haumea would pass directly in front of a distant star from our viewpoint on Earth. By training dozens of telescopes across Europe on this event, they could watch as the star's light winked out, not just once when Haumea itself blocked it, but multiple times. The data revealed a series of tiny, symmetrical dips in the star's brightness just before and after the main occultation. This was the telltale signature of a ring system, a thin band of particles encircling the dwarf planet and briefly dimming the starlight as it passed by. The measurements were incredibly precise, revealing a dense ring about 43 miles wide, sitting over 1,000 miles above Haumea's fractured surface. This immediately raises a profound mechanical question. How does a ring remain stable around such a small, fast-spinning world? The ring particles are likely a mixture of water ice and dark rocky material, debris probably left over from the same ancient impact that gave Haumea its spin. But the physics of their confinement is a real head-scratcher. With such a weak gravitational field, simple orbital mechanics suggest that these particles should have either drifted away into space or spiraled down to the surface long ago. For a ring to persist, something must be acting as a shepherd, corralling the particles and preventing them from dispersing. Around Saturn, small moons like Pan and Daphne's orbit within the rings, their gravity creating gaps and sharp edges. Haumea might have its own unseen, miniature shepherding moonlets, too small for our current telescopes to detect, whose gravitational influence neatly trims and maintains the ring. Another compelling theory involves Haumea's extreme shape. Because it is not a perfect sphere, its gravitational field is uneven, creating strange zones of stability known as orbital resonances. A particle orbiting at just the right distance might be locked into a stable path, where the tugs from Haumea's elongated body cancel out in a way that prevents the particle from drifting. It's a delicate cosmic dance, one that could theoretically maintain a ring without the need for shepherd moons. There's also the possibility that the ring is a relatively new and temporary feature. Perhaps it is the result of a more recent, smaller collision that kicked up fresh debris, and we are simply observing it during a brief window before it dissipates. However, the ring's apparent density and sharp boundaries suggest a degree of stability that argues against a purely transient phenomenon. The existence of this ring forces us to expand our models of celestial mechanics, proving that rings are not the exclusive property of giant planets, and that even in the solar system's frozen outskirts, nature finds astonishingly complex ways to organize matter. And just as every great mystery needs its accomplices, Haumea does not travel alone. Orbiting this tumbling dwarf planet are two tiny, enigmatic moons, Haumea and Namoka, completing a strange and isolated family in the outer darkness. Their discovery in 2005 was a pivotal moment, adding crucial characters to our cosmic detective story. Astronomers using the powerful W.M. Keck Observatory in Hawaii spotted these faint companions, and in a fitting tribute to the mythology of the land where they were discovered, they were named after Hawaiian goddesses. Haumea is the patron goddess of the island of Hawaii and of hula dancers, while Namoka is a water spirit, the sister of Pele, the volcano goddess. But beyond their poetic names, these two small worlds are central to unraveling the violent history of their parent body. Their physical characteristics immediately mark them as something other than typical captured asteroids. Both moons are quite small. Haumea, the larger and outer moon, is only about 250 miles in diameter, while Haumea, orbiting closer in, is less than 100 miles across. More tellingly, they are not round. Like Haumea itself, they are likely irregularly shaped, lumps of rock and ice that never had enough gravity to pull themselves into spheres. This is our first clue that they might not be independent travelers that Haumea snatched from the void, but rather pieces of Haumea itself, born from a singular cataclysmic event. The true mystery of Haumea and Haumea lies in their origin story, and the evidence points strongly toward a dramatic birth. The leading theory suggests they are the direct offspring of the same colossal impact that is thought to have set Haumea spinning so rapidly. In this scenario, the glancing blow that transformed the dwarf planet would have been so violent that it vaporized and blasted enormous plumes of debris into orbit. Over time, the largest fragments within this debris disk would have coalesced through their own gravity, accreting smaller particles to form the two moons we see today. This model elegantly explains several key observations. First, the moons are composed of water ice that is remarkably similar to the crystalline ice found on Haumea's surface, suggesting a shared origin from the same source material. Furthermore, the orbital dynamics of this little system provide some of the most compelling evidence. Haumea and Haumea follow orbits that are not simple, serene circles. Their paths are dynamic and complex, influenced heavily by Haumea's irregular gravitational field, a direct consequence of its football-like shape. Haumea, in particular, has a particularly eccentric and tilted orbit, a configuration that would be highly unlikely if it were a captured object that had drifted into place. Such a chaotic orbit is much more consistent with a formation from a disk of debris, where gravitational interactions with other fragments and with the rapidly spinning Haumea itself could have sculpted these unusual paths. The moons, therefore, are not just silent companions, they are active participants in a gravitational ballet that has been ongoing for billions of years, their movements preserving a frozen record of the impact that created them. While the capture theory that Haumea's gravity snagged two passing Kuiper Belt objects remains a remote possibility, it struggles to account for the compositional similarities and the specific, agitated orbital architecture. Haumea and Haumea appear to be the surviving children of a planetary-scale catastrophe, the last pieces of a puzzle that began with a world-shattering collision in the earliest days of our solar system. While Haumea follows a relatively sedate path, its smaller sibling, Haumea, engages in a far more erratic and unpredictable orbital dance. If the Haumea system were a royal court, Haumea would be a noble in a stable orbit, while Haumea would be a courtier constantly jostled by the whims of the king and the larger noble. Its orbit is not a neat, circular ellipse but a stretched, wobbling, and highly perturbed path that has astronomers scratching their heads. This isn't a simple case of one body orbiting another. It's a complex gravitational tug of war where Haumea is the rope, pulled simultaneously by the dwarf planet's uneven gravity and the persistent influence of its larger sister moon. The primary source of this chaos is Haumea's extremely irregular shape. We've established that it's not a sphere, and this has profound consequences for its gravitational field. Instead of being perfectly symmetrical, pulling equally in all directions, Haumea's gravity is lumpy and uneven. Imagine trying to orbit a football instead of a basketball. Your path would be constantly tweaked and adjusted as you pass near the pointy ends versus the rounded sides. Haumea, orbiting relatively closely, feels these gravitational variations intensely. As it loops around Haumea, the strength and direction of the pull it experiences change dramatically, giving its orbit a characteristic wobble or precession over time. Compounding this already complex situation is the gravitational influence of Haumea. The larger moon's orbit lies further out, but its gravitational reach is significant. As Haumea completes its own chaotic loops, it periodically comes close enough to Haumea for the bigger moon's gravity to give it a significant gravitational kick. These encounters act like periodic nudges, further distorting Haumea's already perturbed path. The result is an orbital resonance, a situation where the orbital periods of the two moons are related by a simple ratio, meaning these gravitational kicks happen at regular, repeating intervals, amplifying their effect over millions of years. This combination of a non-spherical central body and a perturbing sibling moon creates a dynamic environment that is incredibly difficult to model with perfect accuracy. For scientists who specialize in celestial mechanics, known as dynamicists, Haumea's orbit represents a formidable puzzle. Their computer simulations must account for a frantic, tumbling ellipsoid, two moons of different masses, and all the subtle gravitational interactions between them. Small errors in estimating the mass of Haumea or the exact density distribution within Haumea can lead to simulations that quickly diverge from the moon's actual observed path over long timescales. Studying this chaotic dance isn't just an academic exercise, it's a crucial way to weigh these distant worlds. By carefully tracking how Haumea's orbit changes, astronomers can reverse engineer the system, calculating the masses of Haumea and Haumea with greater precision than would be possible otherwise. The moon's erratic path is therefore more than just a curiosity. It is a delicate instrument for measurement, its wobbles and weaves encoding the hidden properties of this most unusual planetary family. But the strangeness of Haumea isn't just in its shape or the dynamics of its moons. It extends right down to the very ground. When astronomers first analyzed the light reflecting off its surface, they expected to see the signature of amorphous ice. This is the kind of ice that should dominate in the deep freeze of the Kuiper Belt, a disorganized glass-like solid where water molecules are frozen in a chaotic jumble. This amorphous ice is the default state for objects in this region, created and maintained by the relentless bombardment of cosmic radiation over billions of years, which constantly damages any orderly crystalline structure. Instead, the spectral data revealed something astonishing. Haumea is covered in a surprisingly pristine, glittering blanket of crystalline water ice. This is the kind of ice we're familiar with on Earth, the ice in snowflakes and glaciers, where the water molecules are arranged in a neat, regular, crystalline lattice. This discovery was profoundly unexpected because crystalline ice is fragile. It can only form and persist at temperatures well above the negative 230 degrees Celsius that is typical for Haumea's orbit. More importantly, it should be quickly destroyed by radiation, its orderly structure blasted back into a disordered, amorphous state within a relatively short period, on the order of tens of millions of years. For a world that has been sitting in the same cold, radioactive environment for over 4 billion years, the presence of fresh, crystalline ice is like finding a perfectly preserved, vibrant painting in an ancient, damp tomb. It simply should not be there, which means something must be actively maintaining it. This presents us with a classic scientific puzzle, a discrepancy between what we observe and what our current models predict. The existence of this young-looking ice points unequivocally to some form of recent geological activity. Haumea, a small, cold dwarf planet, was assumed to be a geologically dead world, a fossil from the solar system's infancy. Yet its surface is telling a different story, one of renewal and change. The most compelling explanation is a process known as cryovolcanism or ice volcanism. Instead of spewing molten rock, a cryovolcano would erupt with a salty, slushy mixture of water, ammonia, or methane. The idea is that Haumea's interior might not be entirely frozen solid. The tremendous energy generated by its rapid spin, combined with heat from the decay of radioactive elements locked within its rocky core, could be enough to maintain a subsurface ocean of liquid water, or at least a warm, slushy layer insulated beneath a thick crust of ice. Occasionally, the pressure in this reservoir could build to a breaking point, forcing this relatively warm slush up through fractures in the crust and onto the surface. There, in the vacuum of space, it would instantly flash freeze, creating a fresh, new layer of beautiful crystalline ice, effectively repaving parts of the dwarf planet and erasing the radiation damage. However, the cryovolcanism theory is not without its own complications. Haumea is quite small, and it has likely lost much of its internal heat over the eons. Sustaining enough geothermal activity to power regular resurfacing events for billions of years is a significant challenge. This leads scientists to consider alternative or perhaps complementary mechanisms. One possibility involves the relentless effects of Haumea's own rotation. The constant gravitational stress and tidal flexing caused by its moons, particularly the chaotic tug of war with Namaka, could generate internal friction heat. This is the same process that keeps the interior of Jupiter's moon Europa warm, and it could be providing just enough energy within Haumea to occasionally melt ice from within. Another, more dramatic idea points back to the system's violent origin. The same family of smaller objects that are thought to be fragments from Haumea's giant impact still share its orbital neighborhood. It is plausible that Haumea is continuously bombarded by tiny impacts from its own kin. These small collisions could be frequent enough to kick up surface material, exposing fresh ice from below that hasn't been exposed to long-term radiation, or even triggering small-scale cryovolcanic eruptions at the impact sites. Each of these scenarios paints a picture of a far more dynamic world than we ever imagined. A tiny, distant dwarf planet that is not a static relic, but a place with its own active, if subtle, geological heartbeat. The crystalline ice is therefore more than just a surface feature. It is a vital sign, a clue that even in the most remote and frozen reaches of our solar system, worlds can harbor surprising secrets and unexpected forms of activity. Now, as if the mysteries of its surface weren't enough, we plunge deeper into Haumea, uncovering a contradiction that challenges our very ideas of how such distant worlds are built. This is the puzzle of its unexpectedly high density. When we consider an object in the frigid Kuiper Belt, we naturally picture a giant, dirty snowball, a loosely packed amalgamation of ice and rock with a relatively low density. But Haumea defies this expectation in a spectacular way. Precise measurements of its mass and volume, calculated by observing the orbits of its moons, reveal a density that is startlingly high, nearly twice that of pure water ice and much closer to the density of rocky planets like Mars. This single number is a profound clue, whispering secrets about what lies hidden beneath the glittering, icy exterior. What this density tells us is that Haumea is not a simple ball of ice. It must have a radically differentiated internal structure. The most widely accepted model suggests a dense, rocky core, possibly rich in silicates and metals, accounting for a significant portion of its total mass. This core is then enveloped by a mantle of water ice, but this icy shell is surprisingly thin relative to the size of the rocky interior. Imagine a world that is, at its heart, more like the terrestrial planets of the inner solar system, which just happens to be wearing a thick, icy overcoat. This structure forces us to reconsider Haumea's entire life story. How did a world that formed in a region dominated by volatile ices end up with the composition of a planet that grew much closer to the warmth of the sun? This brings us to one of the most compelling theories for its origin, planetary migration. The classical view of our solar system's formation is that planets assembled in neat zones, with rock and metal condensing near the sun and ices dominating farther out. But Haumea's rocky heart suggests a more turbulent history. Perhaps it did not form in its current, distant orbit at all. Instead, it may have begun its life much closer to the sun, within the primordial disk of gas and dust that swirled around our infant star. In this warmer environment, it could have started as a protoplanet, accumulating large amounts of rocky material and developing a dense core, just like Earth or Mars. Then, in the solar system's violent youth, a gravitational encounter with a giant planet, most likely Neptune, could have acted as a celestial slingshot, hurling this nascent world outwards into the cold darkness of the Kuiper Belt. Once exiled to this icy realm, it would have then accumulated a new mantle of water ice and other frozen volatiles from the surrounding material, creating the layered world we infer today. However, this migration theory is not the only possibility. An alternative idea suggests that Haumea could have formed right where it is, but under special conditions that allowed it to gather more rock than its neighbors. In the early Kuiper Belt, there may have been a greater abundance of large, rocky planetesimals than we currently observe. If Haumea was one of the largest objects to form in that region, its stronger gravity could have allowed it to sweep up and accrete a disproportionate amount of this available rocky material, leaving smaller, icier objects in its wake. This scenario avoids the need for a dramatic migration event, but it requires that the early Kuiper Belt was somehow enriched with rock, which is itself a complex puzzle. Then, of course, we must reconcile this dense structure with the giant impact hypothesis we discussed earlier. That catastrophic collision, which likely spun Haumea up and created its moons, would have had a profound effect on its interior. The incredible heat generated by the impact could have caused the dwarf planet to fully differentiate, melting the entire body and allowing the heavy rocky material to sink to the center while the lighter ices rose to the surface, a process sometimes called impact-induced differentiation. In this view, the collision wasn't just a shaping event. It was a forge that remade Haumea from the inside out, creating the dense core we detect today. The high density of Haumea is therefore far more than a simple statistic. It is a fundamental property that ties together its spin, its shape, and its surface features, pointing toward a formation history of incredible violence and dynamism, whether it began near the Sun or not. This brings us to a mystery that extends far beyond Haumea itself, connecting it to a whole clan of objects scattered across the Kuiper Belt. We've talked about the giant impact that likely shaped the dwarf planet, but the evidence for that event isn't confined to its rapid spin and orbiting moon. The most compelling proof comes from an entire family of distant worlds that share its cosmic bloodline. Astronomers have identified a unique group of Kuiper Belt objects, often called the Haumea family, that move along strikingly similar orbits and, most tellingly, possess surfaces coated in the same unusually bright crystalline water ice. These are not random neighbors. They are believed to be the scattered fragments, the surviving shrapnel, from that primordial collision billions of years ago. Identifying these distant relatives is like finding pieces of the same pottery at an archaeological site, allowing scientists to reconstruct the size, force, and angle of the impact that created them. The existence of this family is a critical piece of the puzzle. When astronomers look at other impact families in the solar system, like the groups of asteroids linked to massive collisions in the main belt between Mars and Jupiter, they see a pattern. The fragments are typically spread out over a wide range of orbital paths, their orbits perturbed and stretched by gravitational interactions over immense spans of time. The Haumea family, however, defies this expectation. It is remarkably compact and dynamically cold, meaning its members follow very similar, circular orbits that are closely clustered together. This tight grouping is profoundly strange. Given the age of the solar system, you would expect gravitational nudges from giant planets like Neptune to have scattered these fragments far and wide, dispersing the family across the Kuiper Belt. The fact that they remain so close together suggests one of two fascinating possibilities. Either the collision that created them happened much more recently than we thought, perhaps within the last billion years, giving gravity less time to pull them apart, or the event occurred in a peculiarly quiet and protected region of the Kuiper Belt, a gravitational safe zone relatively immune to the disruptive influences of larger planets. This compact nature makes the Haumea family a veritable laboratory for studying planetary collisions. By analyzing the orbits of the known members, which number around a dozen confirmed objects with many more candidates, scientists can essentially rewind the clock. Powerful computer simulations can trace the paths of these fragments backwards in time until they converge, pinpointing the precise location and moment of the impact. This forensic astronomy suggests the collision was incredibly violent, blasting away a significant portion of Haumea's original icy mantle and scattering it across its orbital path. The family members themselves are thought to be primarily composed of pure water ice, as the impact would have stripped away their outer layers, leaving behind chunks of the dwarf planet's interior. This explains why they share Haumea's spectral signature, a match that is almost impossible to explain through any process other than a shared origin. Yet, the mystery deepens when we consider why this family is so distinct. Other large Kuiper Belt objects like Pluto or Makemake show no evidence of such a surrounding family of fragments. This leads to a crucial question. What was so special about Haumea that its collision produced this lasting, identifiable clan, while other dwarf planets seem to have quieter histories? The answer may lie in its unique composition. As we discussed, Haumea has that unusually large, dense rocky core. An impact into a body with this structure would have been fundamentally different from a collision between two more generic, icy Kuiper Belt objects. The energy transfer and the way material is ejected could have been far more efficient, creating a larger cloud of debris that was then able to coalesce into stable fragments rather than just dispersing as dust. The Haumea family, therefore, is more than just evidence of a past catastrophe. It is a unique celestial phenomenon, a tightly knit group of siblings preserving the story of their violent birth in a way that no other known family in the outer solar system does. Their continued study offers a rare window into the chaotic processes that built not just Haumea, but the entire Kuiper Belt. This shared composition is our first major clue to the nature of the explosion itself. When a colossal impact occurs, it doesn't just break a world apart randomly, it peels it back like an onion. The energy of the collision is so immense that it preferentially blasts away the outermost layers. In Haumea's case, this would have been its relatively thin mantle of water ice. The debris cloud from such an event would therefore be heavily enriched with this surface material, while the heavier, denser rocky core of the progenitor body would have remained largely intact, becoming the Haumea we see today. The family members, then, are not chunks of the whole world. They are specifically pieces of its icy shell, flung into space and left to orbit the sun as permanent reminders of the catastrophe. This explains the remarkable spectral uniformity. They all come from the same source layer, a gigantic reservoir of crystalline ice that was shattered and scattered across the void. It's a level of consistency that would be astronomically improbable if these objects had simply formed independently near each other. They are literal cousins sharing the same cosmic DNA. Yet the plot thickens when we move from what they are made of to where they are now. The orbital distribution of these fragments is the second part of this intertwined mystery, and it presents a fascinating challenge. The fact that these objects are still clustered together, following very similar paths around the sun, is like finding a crime scene that has been perfectly preserved for billions of years. Their orbits are a frozen record of the precise moment of the impact, encoding information about the explosion's force and direction. By carefully mapping their current positions and velocities, astronomers can run sophisticated computer simulations, effectively rewinding the solar system's clock to witness the cataclysm in reverse. The goal is to start with the scattered family we see today and find the single initial configuration from which they all originated. However, this cosmic forensics is incredibly difficult. The main complication is Neptune. The giant planet's immense gravity dominates the outer solar system, and over billions of years, its subtle but persistent gravitational tugs should have progressively perturbed the orbits of these smaller fragments. Like a giant stirring a pot, Neptune's influence would be expected to have dispersed the family, smearing their orbits out into a much wider and more chaotic distribution. The fact that the family remains so tightly clustered is therefore a paradox. It suggests that either the collision happened much more recently than we assume, giving Neptune less time to disrupt the group, or that the explosion placed the fragments into a peculiarly stable orbital configuration, a sweet spot in the gravitational landscape that is somehow resistant to Neptune's disruptive influence. Some models even suggest that the family's orbits are in a specific resonance with Neptune, meaning their orbital periods are synchronized in a way that protects them from being scattered, a delicate gravitational dance that has preserved their grouping against all odds. Every attempt to model this ancient event must account for a dizzying number of variables: the exact size and speed of the impactor, the angle of collision, the internal structure of the proto-Haumea, and the subsequent gravitational influences of every major planet over 4 billion years. Small changes in any of these parameters can lead to wildly different outcomes in the simulation. The challenge is to find the one unique set of initial conditions that, after running the clock forward, results in the exact orbital distribution we observe today. It's a painstaking process of trial and error that continues to occupy some of the brightest minds in planetary science. The Haumea family, therefore, is not just a collection of rocks. It is an exceptionally complex and long-running physics problem, a celestial puzzle box whose solution will reveal not only the violent history of one dwarf planet, but also the subtle gravitational rules that govern the entire outer solar system. From the shattered family of icy fragments, we now turn our attention to the sky above Haumea itself, or more accurately, the profound lack of one. This brings us to our 11th great mystery, the case of the missing atmosphere. In the cold depths of the Kuiper Belt, the very concept of an atmosphere seems almost paradoxical. How could a tiny, frozen world so far from the sun's warmth possibly hold onto a gaseous envelope? Yet for Haumea, the question is not so simple, and the answer, much like the dwarf planet itself, is shrouded in fascinating complexity. Current evidence points not to a complete absence of air, but to something far more elusive, a transient, whisper-thin atmosphere that may come and go with the seasons of its long, lonely year. The possibility of such a tenuous atmosphere hinges entirely on the peculiar nature of its orbit. Like all solar system bodies, Haumea's path around the Sun is an ellipse, not a perfect circle. This means its distance from the Sun varies significantly over the course of its 285 Earth-year orbit. At its closest approach, a point called perihelion, Haumea ventures to within about 34 astronomical units of the Sun. While this is still incredibly distant, it's close enough for the feeble sunlight to provide a minuscule amount of heat. This tiny warmth can be just sufficient to cause a process called sublimation, where the crystalline water ice on its surface transforms directly from a solid into a gas, skipping the liquid phase entirely. For a brief period around this perihelion, Haumea might effectively be outgassing, surrounding itself with a temporary shroud of water vapor and other volatile gases that have sublimated from its surface. Detecting this ghost of an atmosphere is a monumental challenge that pushes our observational technology to its absolute limits. It cannot be seen directly. Instead, astronomers rely on the same sophisticated technique that revealed its ring, the stellar occultation. They patiently wait for Haumea to pass in front of a bright, distant star. As the starlight is extinguished by the dwarf planet's solid body, scientists meticulously analyze the light's behavior just before and after the main event. If even a whisper of gas is present, it will cause a very gradual dimming of the starlight, a subtle fade-in and fade-out effect, rather than the sharp, instant cutoff produced by a solid surface with no air. Capturing this data requires immense precision and a fair amount of luck, as the occultation paths are narrow and the events are fleeting, So far, the evidence for this transient atmosphere remains ambiguous, with some occultation data hinting at its presence while other observations show no definitive sign. This inconsistency itself is a clue supporting the idea that the atmosphere is not permanent, but appears and dissipates depending on Haumea's position in its orbit. The real scientific puzzle, however, is not just if this atmosphere exists, but how it can possibly behave. Haumea's extremely weak gravity, a consequence of its small size, means it has a very low escape velocity. Any gas molecule that manages to jump off the surface finds it remarkably easy to simply drift away into space forever. For an atmosphere to persist, even temporarily, the rate of sublimation from the surface must, for a time, exceed the rate at which molecules are escaping into the void. This creates a delicate and dynamic balance. When Haumea is near perihelion and relatively warm, sublimation might briefly win, creating a detectable, if incredibly thin, atmospheric layer. As it moves back toward the cold of aphelion, the farthest point from the Sun, the sublimation shuts down almost completely, and the escape of molecules quickly strips away whatever tenuous envelope had formed. This cycle of birth and loss would make Haumea's atmosphere one of the most ephemeral in the entire solar system, but the mysteries don't end with simple sublimation. Haumea's rapid rotation adds another bizarre twist to this atmospheric drama. On a slow-spinning world like Earth, our atmosphere is distributed fairly evenly by weather patterns. On Haumea, its 4-hour day creates immense centrifugal force at the equator, which could dramatically affect how any atmosphere behaves. It's possible that the gaseous envelope is not a uniform sphere, but is instead concentrated around the poles, where the rotational flinging is minimized, leaving the equatorial regions effectively exposed to space. Alternatively, the constant tumbling could churn the thin atmosphere, creating unpredictable and exotic weather patterns unlike anything we've ever modeled. Then there is the potential role of its crystalline ice. This unusually pure and reflective ice might sublimate differently than the darker, amorphous ice found on other Kuiper Belt objects, perhaps releasing gas in more localized or explosive ways like tiny geysers. The quest to characterize Haumea's missing atmosphere is therefore a quest to understand the ultimate limits of planetary climate science, a study of air so thin and fleeting that it defies our conventional definitions, yet whose presence or absence holds critical clues to the ongoing geological activity and volatile inventory of this most perplexing of worlds. Just when we think we have a handle on Haumea's overall composition, its own light tells a different, more complex story. This leads us to the enigma of its extreme and fluctuating brightness. Most objects in the Kuiper Belt are dark, dull worlds, reflecting only a small fraction of the sunlight that reaches them. Haumea, by contrast, is a dazzling outlier. Its surface albedo, or reflectivity, is exceptionally high, rivaling that of freshly fallen snow. This intense brightness is a direct result of that pristine, crystalline water ice we discussed, which acts like a vast cosmic mirror. But the real mystery isn't just how bright Haumea is, but how that brightness changes. As the dwarf planet completes its frantic 4-hour rotation, the amount of light it reflects back to Earth varies dramatically. This isn't a subtle flicker, it's a significant rhythmic pulsation, a beacon in the darkness whose signal strength rises and falls with clockwork precision. For astronomers, this light curve is a cryptic message, a pattern of flashes that holds the key to mapping the surface of a world we cannot yet see directly. Decoding this message is a monumental challenge. The variations in brightness are our only tool for inferring what the actual terrain looks like. The principle is straightforward. Different surface features reflect light differently. A smooth, uniform sphere would produce a flat, unchanging light curve. Haumea's wild fluctuations immediately tell us its surface is anything but uniform. The primary question is what specific features are causing these changes. Scientists have proposed several compelling theories, each painting a different picture of this tumbling world. The first and most intuitive idea involves variations in surface composition. Perhaps Haumea is not uniformly covered in bright ice. There could be vast, dark patches, regions where the pristine ice has been contaminated by dust or where underlying, darker rock is exposed. As the dwarf planet spins, these dark and bright regions rotate in and out of view from Earth, causing the overall brightness to rise and fall. This would be similar to watching a tumbling ball that is half painted black. From our perspective, its apparent brightness would change depending on which side is facing us. A second, more dramatic possibility points to major topographical features. Haumea's rapid rotation and potential for past geological activity make the existence of large-scale structures entirely plausible. Imagine a massive impact crater, a vast basin so large it covers a significant portion of one hemisphere. The interior of such a crater might be rougher or contain different materials, making it less reflective than the surrounding plains of bright ice. Alternatively, the extreme forces that shaped Haumea could have thrust up a great mountain range or created a series of deep fractures. The shadows cast by these towering features, or the different reflective properties of their slopes, could easily account for the observed changes in light. We see this effect on other irregularly shaped asteroids, where large craters or ridges create distinct signatures in their light curves. However, there is a third, more subtle explanation that ties directly into Haumea's most fundamental oddity, its shape. The football-like ellipsoid itself could be the primary cause of the brightness variation. Think about the geometry. The surface area presented to Earth changes as Haumea rotates. When we are looking at its long, bulging equator, we see a larger, more spread-out surface. When it turns and presents one of its pointy poles, we are looking at a much smaller, more compact cross-section. Even if the surface were perfectly uniform in composition, this change in apparent size alone would cause a rhythmic variation in brightness. The challenge for astronomers is to disentangle this geometric effect from the signatures of actual surface features. It's a difficult puzzle, requiring sophisticated computer models that simulate the light reflecting off a spinning ellipsoid of known dimensions, and then subtracting that predicted curve from the one we actually observe. Any remaining fluctuations are the true fingerprints of its geology. This is where the immense difficulty of remote observation becomes starkly clear. With current technology, Haumea is little more than a single, brilliant pixel of light in our most powerful telescopes. We cannot resolve its surface, we cannot see its craters or mountains. Every piece of information we have about its topography is inferred indirectly from these delicate photometric measurements. Each tiny dip and peak in its light curve is a precious data point, and interpreting them is an exercise in extreme deduction. It's like trying to determine the shape and texture of a room by watching the faint, changing glow of a single candle shining through its keyhole. The variations we see are consistent with several models, and without a closer look, we cannot be certain which is correct. It is entirely possible that all these factors are at play: a non-spherical shape, dark compositional patches, and dramatic topography all working together to create the complex light signature of this spinning celestial diamond. The mystery of its brightness variations is a testament to the limits of our current vision, a tantalizing hint of a complex and varied landscape that remains, for now, just beyond our sight. But the presence of that fresh, crystalline ice points to something even more dynamic than just a one-time collision. It suggests an internal engine, a source of heat that could be driving geological processes even today. This leads us directly to our 13th mystery, the tantalizing possibility of active cryovolcanism on Haumea. The term itself sounds like science fiction, ice volcanoes. Instead of erupting with scorching, molten rock, a cryovolcano would spew a frigid, slushy mixture of water, ammonia, methane, or other volatile compounds. On a world like Haumea, where surface temperatures are barely above absolute zero, this would be the dominant form of geology, a slow-motion spectacle of freezing fury. The mechanics of such an event would be utterly alien compared to anything on Earth. Imagine not a fiery mountain, but a vast, gentle dome or a fissure in the icy crust. Deep below the surface, pressure builds in a pocket of liquid water, kept from freezing by some internal heat source. When the overlying ice can no longer contain the stress, it fractures. The result is not a violent explosion, but more of a slow, oozing eruption. A thick, salty slush, perhaps mixed with ammonia that acts as a natural antifreeze, would creep out onto the surface. In Haumea's incredibly low gravity, this material might not even flow like lava. It could be flung into space in graceful, arcing fountains, creating temporary, glittering plumes that fall back to the ground as a fresh layer of snow like crystalline ice. This process would be a perfect explanation for the surprisingly young appearance of its surface, constantly repaving and renewing the ice, erasing the scars of radiation and ancient impact. The central question, then, is what could possibly be generating the necessary heat to power these icy eruptions? For a small, distant world assumed to be geologically dead, this is the core of the mystery. One potential source is the ancient heat from the decay of radioactive elements locked within its dense rocky core. Elements like uranium, thorium, and potassium have been slowly releasing energy for billions of years. While this radiogenic heating is a factor for all rocky bodies, the critical factor is insulation. Haumea's thick mantle of water ice could be acting as a superb blanket, trapping that residual heat and preventing it from escaping too quickly, allowing a subsurface ocean or at least localized pockets of slushy brine to persist to this day. Another, more compelling heat source involves the relentless forces acting upon Haumea from the outside. We've already seen the chaotic gravitational dance of its moon Namaka. That same orbital turbulence doesn't just affect the moon's path, it also works on Haumea itself. The gravitational tugs from its moons, particularly as Namaka moves through its eccentric orbit, stretch and flex the dwarf planet's interior. This constant kneading, known as tidal heating, generates friction and thus heat. It is this very process that keeps the interiors of moons like Jupiter's Europa and Saturn's Enceladus warm enough to maintain global subsurface oceans. While the tidal forces on Haumea are weaker than those exerted by a gas giant, they are persistent over billions of years and could provide just enough energy to melt ice at the boundary between the rocky core and the icy mantle. Then there is the wild card of Haumea's own incredible rotation. The colossal centrifugal force generated by its 4-hour day doesn't just shape its exterior, it could also be stirring its interior. This relentless spinning could create internal currents and stresses within the malleable ice and rock, generating heat through a process called shear heating. It's analogous to how rubbing your hands together warms them up, but on a planetary scale. This unique combination of tidal flexing and rotational stress presents a heat generation recipe that is entirely unique to Haumea, setting it apart from other Kuiper Belt objects. Proving any of this, however, is the ultimate challenge. Without a dedicated spacecraft mission to fly by and measure heat emissions from its surface, the evidence for cryovolcanism remains circumstantial. A brilliant hypothesis born from the need to explain the impossible youth of a world that should have been frozen in time. And now we come to a mystery that seems simple on the surface but reveals layers of complexity. What is the true color of Haumea? When we picture this distant world, a brilliant, glittering white ball of ice might come to mind given its high reflectivity. But the reality is far more nuanced. Precise photometric studies show that Haumea is not a pure, featureless white. Instead, it appears as a neutrally colored world, a kind of dull gray, but with a subtle, persistent reddish tint, particularly in certain wavelengths of light. This faint blush is a crucial clue, a stain upon the ice that hints at chemical processes playing out across billions of years in the deep freeze of space. The pristine water ice accounts for the brightness, but this reddish coloration tells a different story. one of contamination and transformation driven by the harsh environment of the Kuiper Belt. The prime suspect for causing this reddish hue is a class of complex organic compounds known as tholins. This isn't a single substance, but rather a catch-all term for a sticky, tar-like mixture of molecules that form when simple ices are bombarded by high-energy radiation. The process is a slow cosmic chemistry experiment. Imagine the surface of Haumea continuously exposed to the relentless barrage of cosmic rays and solar wind over eons. This radiation has enough energy to break apart the stable molecules in the surface ice, like methane or nitrogen, that might be mixed in with the water. These broken fragments, now highly reactive radicals, then randomly recombine into new, more complex polymers and organic compounds, the tholins. These substances are famously reddish-brown and are thought to be responsible for the distinctive colors of many other Kuiper Belt objects, like Pluto's reddish patches and the dark, rust-colored terrain of Makemake. On Haumea, the tholin layer might not be a continuous blanket, but could exist in patches or as a thin film dusted across the brighter ice, accounting for the overall subtle tint rather than a dramatic color change. However, the tholin hypothesis is not without its complications. The presence of these compounds requires that Haumea's surface contains other ingredients besides water ice. There needs to be a source of carbon, likely in the form of methane ice or nitrogen, or even more complex hydrocarbons. Yet, spectroscopic observations have had a surprisingly difficult time conclusively identifying these other ices on Haumea's surface in significant quantities. The spectral signature is dominated by the strong, clear features of water ice. This raises an alternative possibility. Perhaps the reddish color comes from something entirely inorganic. It could be caused by silicate minerals, or more specifically, by iron-bearing minerals mixed within the ice. Just as rust gives Mars its red color, tiny particles of iron oxide embedded in Haumea's crust could impart a similar reddish tint. Alternatively, the constant radiation bombardment could be affecting not just organic molecules, but the crystalline structure of the ice itself, creating radiation-damaged zones that absorb light differently and produce a colored appearance. The true mystery, then, is not just identifying the coloring agent, but understanding why it's so subtle. If tholins are forming, why hasn't Haumea turned a darker, more uniform red like some of its neighbors? This brings us back to the idea of geological renewal. The very processes that maintain the bright, crystalline ice, whether cryovolcanism or minor impacts, could be constantly refreshing the surface, burying or erasing the dark, red tholins almost as quickly as they form. The faint reddish tint we see could represent a delicate balance, a snapshot of this ongoing battle between the radiation that darkens the surface and the internal activity that repaves it with bright, new ice. The color of Haumea is therefore not a static property. It is a dynamic indicator, a visible record of the constant interplay between external radiation and internal heat. Decoding its exact shade could tell us not only what chemicals are present on the surface, but also the rate at which that surface is being renewed, offering a unique window into the ongoing geological life of this enigmatic dwarf planet. Moving from the subtle color of its surface to the fundamental orientation of its spin, we encounter yet another layer of Haumea's strangeness, the peculiar tilt of its axis. Every planet in our solar system, including Earth, is tilted to some degree relative to the plane of its orbit. This axial tilt is what gives us our seasons. But as with so many things, Haumea doesn't follow the standard pattern. While Earth is tilted at a familiar 23.5 degrees and Uranus is knocked over on its side at a dramatic 98 degrees, Haumea presents a truly curious case. Its axis is tilted at an angle that is both extreme and yet difficult to pin down with absolute precision, estimated to be roughly 126 degrees. To understand what that means, picture a spinning top. Now, imagine that top is not just wobbling slightly, but is almost completely inverted, spinning nearly on its side with its poles pointing almost directly toward the sun during parts of its long year. This bizarre orientation is far more than a simple factoid. It is a profound clue about the most violent event in this dwarf planet's history. The most compelling explanation for this extreme tilt points directly back to the same cataclysmic impact that is thought to have shaped so many of its other features. The giant impact hypothesis offers a unified answer to multiple mysteries. The colossal, glancing blow that supposedly set Haumea spinning at a breakneck pace would not have just transferred angular momentum. It would have delivered a tremendous torque, a twisting force that could have literally knocked the entire world off its original axis. The angle and force of the impactor would have been the primary factors determining the final tilt. Think of it not just as a billiard ball being struck, but as a globe being hit a staggering blow from the side, sending it tumbling through space with a completely new orientation. This single event origin story is elegant because it ties the spin, the shape, and the tilt together into one coherent narrative of a formative catastrophe. However, alternative theories exist suggesting a more gradual process. In the early solar system, gravitational interactions between protoplanets were common and incredibly powerful. Haumea could have experienced a series of close encounters with other large Kuiper Belt objects, each gravitational tug subtly altering its axial orientation over millions of years until it reached its current extreme state. Another fascinating possibility involves the gravitational influence of Neptune. As Haumea migrated to its current orbit, a complex dance with the giant planet could have gradually torqued its axis through a process called spin-orbit resonance. Yet, these gradualist theories struggle to account for the specific combination of an extremely fast rotation and an extreme tilt. The impact scenario remains the most parsimonious explanation, as it efficiently creates both conditions in one swift, violent event. This dramatic tilt has fascinating consequences for any hypothetical seasons on this frozen world. A Haumean year is 285 times longer than an Earth year. This means each season, driven by the axial tilt, would last for decades, but these would be seasons unlike any we know. During its summer solstice, one of Haumea's poles would be pointed almost directly at the distant sun, experiencing a continuous, if feeble, daylight for many Earth years. Meanwhile, the opposite hemisphere would be plunged into an equally long, deep winter of total darkness. The equatorial regions would see the sun skim low on the horizon, creating long, drawn-out periods of twilight. The intensity of these seasons would be muted by the incredible distance from the sun. The temperature difference between summer and winter would be minuscule by terrestrial standards. But the variation in sunlight could still drive important processes. For instance, the pole facing the sun might experience a slight increase in sublimation, the process where ice turns directly to gas, potentially thickening its transient atmosphere for a few decades before the long winter freezes it all out again. The extreme tilt, therefore, isn't just a historical relic. It actively influences the environmental conditions on this distant world, adding another layer of complexity to its already mysterious nature. Looking ahead into the deep future, we confront a mystery that is fundamentally about time itself, the long-term stability of Haumea's frantic spin. The laws of physics tell us that nothing lasts forever, and a rotation as extreme as Haumea's seems like a prime candidate for eventual decay. The central question is whether we are witnessing a fleeting moment of cosmic hyperactivity or a stable configuration that has endured and will continue to endure for eons. The answer lies in a complex gravitational tug-of-war, a subtle dance of energy transfer between the dwarf planet, its moons, and even its delicate ring. The primary mechanism that could be applying the brakes to Haumea's spin is tidal friction. We see this process in action right here in our own solar system. Earth's gravity creates tides in the oceans of the Moon, but since the Moon is solid, the effect manifests as a slight, continuous flexing of its crust. This friction slowly saps orbital energy, and the result is that the Moon's rotation has gradually slowed until it became tidally locked, now showing us only one face. A similar process is likely at work in the Haumea system, but with fascinating complications. The gravitational pull of its moons, particularly the chaotic Namaka, creates tidal bulges on Haumea's surface. As the dwarf planet spins rapidly beneath these moons, these bulges are constantly being raised and then dragged along. The internal friction generated by this relentless flexing acts like a brake, converting the rotational energy of Haumea into heat within its interior and, in turn, transferring angular momentum to the moons, causing their orbits to slowly expand outward. If this were the only factor at play, we could confidently predict that Haumea's spin is imperceptibly winding down. However, Haumea's unique properties introduce profound complications to this simple model. Its extremely elongated shape is a game changer. A sphere has a predictable and symmetrical gravitational field, but an ellipsoid like Haumea has a lumpy, uneven field with distinct gravitational highs and lows. This creates zones of stability known as spin-orbit resonances. It is possible that Haumea's current rotation rate is not arbitrary, but is instead locked into one of these resonant states. In this configuration, the gravitational tugs from its moons might actually reinforce and stabilize the spin, rather than disrupting it. The system could have settled into a dynamic equilibrium where the loss of energy from tidal friction is perfectly balanced by the way the moon's gravity interacts with Haumea's peculiar shape. It's a delicate balance, but one that could, in theory, remain stable for billions of years. Then we must consider the ring. This tenuous band of particles is not just a passive ornament, it is an active participant in the system's energy budget. The particles within the ring are in orbit, and their motion is influenced by Haumea's gravity and rotation. As they collide with one another and interact gravitationally, there could be a slow but steady exchange of angular momentum between the ring and the central body. In some scenarios, the ring could actually be feeding energy into Haumea's rotation, helping to maintain its high speed against the braking force of tidal friction. Alternatively, the ring could be a net drain on the system, its particles slowly spiraling inward and transferring their angular momentum back to Haumea in a way that actually slows its spin. The precise outcome depends on factors we don't yet fully understand, like the exact mass and density of the ring and the nature of the interactions within it. Projecting the future of this system requires extraordinarily complex computer simulations that account for all these variables simultaneously. A tumbling ellipsoid, 2 moons on perturbed orbits, a ring of unknown mass, and the subtle effects of solar gravity over timescales longer than human history. Small changes in the initial assumptions can lead to wildly different futures. One simulation might show Haumea gradually slowing over the next billion years, eventually becoming locked with one face permanently turned toward Hyaka. Another might show its current state remaining essentially unchanged for the rest of the lifespan of the Sun. This mystery is a stark reminder that even with our advanced knowledge of physics, predicting the ultimate fate of such a complex and unique system remains an immense challenge. The stability of Haumea's spin is not just a question about one dwarf planet. It is a test of our ability to model the intricate and long-term gravitational ballet that governs the lives of all celestial bodies. Peering through the icy crust and into the heart of Haumea, we confront a mystery as fundamental as its shape: what lies beneath the surface. While its high density tells us it must have a dense core and a lighter mantle, the precise architecture of its interior remains a shadowy realm of educated guesswork. The simplest model, based on our understanding of planetary formation, paints a picture of a differentiated world. In this view, Haumea possesses a substantial core composed primarily of silicate rock and metals, a relic of its formation that houses most of its mass. Encasing this core is a thick mantle of water ice, which itself is topped by a relatively thin crust of the pristine, crystalline ice we observe. Yet, this basic layered structure is almost certainly an oversimplification. The true arrangement could be far more complex, shaped by the violent processes that defined its history. The giant impact that likely spun Haumea up would have generated temperatures hotter than the surface of the sun, at least momentarily. This incredible influx of energy could have caused a wholesale melting of the entire body, allowing for a complete and thorough differentiation. Heavy materials would have sunk like stones to form a compact, homogeneous core, while the lighter ices rose to create a uniform mantle. However, if the collision was less energetic, or if Haumea cooled very rapidly afterward, the differentiation might be incomplete. We could be looking at a world with a more heterogeneous interior, where large chunks of rock are still entangled within the icy mantle, or where the core itself is a rubble pile loosely held together by gravity. The extreme elongation of Haumea adds another layer of complexity, suggesting that its internal density might not be evenly distributed. The rocky core itself could be stretched into an ellipsoid, or perhaps the intense centrifugal force has caused heavier materials to migrate toward the equator, creating an internal structure that is as lopsided as its external form. Without seismic data or detailed gravity field measurements from a passing spacecraft, the interior of Haumea remains a planet-sized black box, its secrets locked deep within. This brings us to one of the most thrilling and consequential questions in all of planetary science. Could this distant, frozen world harbor a liquid water ocean? The idea seems preposterous at first glance. Haumea orbits in a region of the solar system where temperatures hover near absolute zero, a place where water should be frozen solid for eternity. Yet, the evidence for geological activity and the presence of young ice strongly suggest that something is providing heat. The possibility of a subsurface ocean is no longer the stuff of pure science fiction. It is a serious scientific hypothesis that, if proven, would radically alter our understanding of where life could potentially arise. For a liquid ocean to exist, two critical conditions must be met: a heat source to melt the ice, and an insulating layer to prevent that heat from escaping too quickly. Haumea has several potential candidates for providing that vital warmth. The first is the residual heat from its formation and the subsequent giant impact. While this primordial heat would have been immense, much of it would have radiated away into space over billions of years. However, if Haumea's rocky core is rich in radioactive elements like uranium, thorium, and potassium, their ongoing decay could provide a steady, long-lasting geothermal furnace. This radiogenic heating is a slow burn, but over the age of the solar system, it could be sufficient to maintain liquid water at the boundary between the rocky core and the icy mantle, especially if the overlying ice acts as an effective insulator. Perhaps a more potent and dynamic heat source is tidal heating. We've already seen the gravitational chaos caused by its moon Namaka. That same gravitational tug of war doesn't just affect the moon's orbit, it works on Haumea itself. The varying pull from its moon stretches and compresses the dwarf planet's interior. This constant flexing generates internal friction, and friction produces heat. This process is what keeps the global oceans of moons like Europa and Enceladus liquid despite their great distance from the Sun. While the tidal forces on Haumea are weaker than those exerted by a gas giant, they are persistent and could be amplified by orbital resonances between Hioka and Namaka. Furthermore, Haumea's own rapid rotation contributes to this internal churning. The colossal centrifugal forces could be stirring its interior, generating additional shear heat, creating a unique combination of warming mechanisms not found on more sedate worlds. The implications of a subsurface ocean are staggering. A layer of liquid water, potentially dozens of kilometers deep, would be a protected environment, shielded from the harsh radiation and impactors of space. If this ocean is in contact with a rocky seafloor, hydrothermal vents could provide a steady supply of chemical nutrients, not unlike those on Earth's ocean floor that support vast ecosystems entirely independent of sunlight. While the presence of such an ocean does not mean life exists on Haumea, it immediately elevates this strange, tumbling world from a geological curiosity to a potential astrobiological target. It suggests that the conditions for habitability, liquid water, chemistry, and a source of energy might be found in the most unexpected corners of our solar system, far from the traditional habitable zone of stars. The search for Haumea's hidden ocean is therefore a quest to understand the ultimate resilience of life itself, and a reminder that beneath a frozen, fractured exterior, the most profound secrets may still be waiting, warm and alive. This brings us to a challenge that seems deceptively straightforward, simply figuring out how big Haumea actually is. You would think that measuring a world, even a distant one, would be one of the first and easiest tasks for astronomers. But with Haumea, nothing is ever simple. The quest to pin down its exact dimensions is a story of precision, frustration, and the stark limitations of observing a tiny, flickering point of light from over 4 billion miles away. The numbers we often see, a length of roughly 1,400 miles and a width of about 700 miles, are not fixed certain values. They are the best estimates from a constant tug of war between different observational techniques, each with its own strengths and inherent uncertainties, and the discrepancies between them are small but scientifically significant. The primary reason this is so difficult boils down to two fundamental problems: its shape and its distance. Because Haumea is not a sphere, we cannot simply measure its diameter and be done. Instead, we have to determine its triaxial ellipsoid dimensions, its length, its width, and its depth. It's like trying to measure the exact proportions of a tumbling football from a vantage point so far away that it's just a speck of light. The main method for this incredibly precise work is the stellar occultation, the same technique that revealed its ring. When Haumea passes in front of a star, the way the starlight winks out tells a detailed story. The duration of the occultation reveals the size of the object along that specific chord or cross-section. By observing multiple occultations from different angles as Haumea rotates, astronomers can slowly piece together a three-dimensional model of its shape, like a sculptor revealing a form from a block of marble by taking measurements from many directions. This method is powerful, but it relies on a perfect alignment of Earth, Haumea, and a background star, events that are rare and require a global network of telescopes to capture successfully. The other major technique involves thermal measurements. All objects emit infrared radiation or heat based on their size and temperature. By using powerful telescopes like the Herschel Space Observatory or the Spitzer Space Telescope, astronomers can measure the total infrared flux coming from Haumea. Since we have a good estimate of its surface temperature from its distance from the Sun, we can then work backwards to calculate its total surface area and from that its size. The problem is that this method assumes the object is a perfect, uniform emitter, which Haumea is not. Its surface is a patchwork of bright, cold ice and potentially darker, slightly warmer regions, and its extremely rapid rotation means its temperature might not be evenly distributed. These complications can introduce small but important errors into the calculation, and this is where the mystery truly lies. The size measurements from occultations and thermal observations don't always agree perfectly. They might be off by just a few dozen miles, but in the world of precise planetary science, that difference matters immensely. Why? Because the exact size is the key that unlocks our understanding of Haumea's most fundamental properties. To calculate its density, you need two things: its mass and its volume. We can determine its mass with high precision by watching the gravitational dance of its moons, Hioka and Namoka. Their orbital periods give us a very accurate measure of how much mass is pulling on them, but volume is derived directly from the dimensions. If our size estimate is even slightly too large, we overestimate the volume, which leads to an underestimation of the density. Conversely, if we underestimate the size, we calculate a density that is artificially high. This is not just an academic exercise. The density is our primary clue to Haumea's internal structure. Is it a loosely packed pile of rubble or a fully differentiated world with a dense, rocky core? A difference of just 5 or 10% in the calculated density could tilt the evidence significantly toward one scenario or the other. A slightly higher density would strongly support the idea of a massive, metal-rich core, reinforcing the planetary migration theory that suggests Haumea formed in the inner solar system. A slightly lower density might indicate a more porous interior or a larger proportion of ice, suggesting it accreted more locally in the Kuiper Belt. The ongoing challenge of nailing down its exact size is therefore central to every other mystery we've explored. It affects our models of the giant impact, our understanding of its internal heat, and even our speculation about a potential subsurface ocean. Every new occultation observed is a chance to refine the numbers, to shrink the error bars, and to bring us one step closer to seeing this enigmatic world not as a blurry pixel, but in its true, sharp, and wildly tumbling proportions. The question of Haumea's birthplace forces us to look back to the very beginning, to a time when the solar system was a swirling, chaotic disk of gas and dust, a cosmic construction zone where the rules were being written in real time. The prevailing theory for how our planetary neighborhood formed is the nebular hypothesis, which paints a picture of order emerging from chaos. In this model, the young sun was surrounded by a protoplanetary disk where temperature dictated composition. Close to the sun's heat, only metals and rocky minerals could condense, leading to the formation of the dense terrestrial planets like Earth and Mars. Farther out beyond the frost line, temperatures were low enough for volatile ices like water, methane, and ammonia to freeze solid, allowing the gas giants and icy worlds to accumulate. By this logic, an object like Haumea, with its massive rocky core, should have formed in the warmer, rock-rich region inside the orbit of Jupiter. Its presence in the icy Kuiper Belt is therefore a major anomaly, a world that appears to be in the wrong part of town entirely. This contradiction is the heart of the scattering theory, a dramatic narrative of planetary pinball that has gained significant traction. The early solar system was not the orderly place it is today. It was a violent arena where newly formed giant planets jostled for position. According to the popular NICE model, a gravitational instability caused Jupiter and Saturn to fall into a specific orbital resonance, their synchronized gravity acting like a wrecking ball that destabilized the entire outer system. This event would have sent Uranus and Neptune migrating outward, and in the process, their immense gravity would have scattered a vast population of icy planetesimals in all directions. Some were flung inward to become comets in the inner solar system, while others, like Haumea, were hurled outward into the distant reaches where they reside today. In this scenario, Haumea is an exile, a world that formed in the comparative warmth of the region between the orbits of the giant planets, only to be violently evicted to the frozen outskirts billions of years ago. Its rocky core is the key piece of evidence, a relic of its original, warmer birthplace that it carried with it into the deep freeze. However, the scattering theory is not without its own set of puzzles. If Haumea was formed closer in and then scattered outward, why does it share such a strong compositional link with other classical Kuiper Belt objects through its family? One would expect an interloper from a different formation region to have a distinct chemical signature, yet the spectral match between Haumea and its family members is remarkably precise. This has led some scientists to champion an alternative, the in situ formation theory. This idea posits that Haumea formed right where we find it, but under special conditions that allowed it to gather more rock than its neighbors. Perhaps the early Kuiper Belt was not as homogeneously icy as we assume. it's possible that it contained a population of larger, rocky planetesimals that had previously migrated outward from the inner solar system. If Haumea was one of the first and largest objects to form in that region, its stronger gravity could have allowed it to act as a local gravitational vacuum cleaner, efficiently accreting a disproportionate amount of this scarce rocky material. It would have grown a massive core not by forming near the Sun, but by monopolizing the available heavy elements in its immediate vicinity, leaving smaller, icier objects in its wake. Choosing between these two origin stories is incredibly difficult because the evidence is, in a way, frozen in time. The chaotic migration events hypothesized by the NICE model occurred over 4 billion years ago, and all the direct forensic evidence has long since been erased or rearranged. The clues we have are circumstantial. Proponents of scattering point to Haumea's orbital characteristics. Its orbit is slightly eccentric and tilted compared to the classical Kuiper Belt, which could be a fingerprint of a disruptive gravitational encounter with a giant planet. Those who argue for in situ formation counter that its orbit is not chaotic enough. If it had been violently scattered, we might expect a more extreme path. They also point to the incredible difficulty of scattering an object as large as Haumea without shattering it completely or ejecting it from the solar system altogether. The debate often comes down to a battle of computer simulations, with researchers tweaking countless variables to see which initial conditions, a calm local birth or a violent migration, best reproduce the Haumea system we observe today. The mystery of its formation location is therefore more than a question of geography. It is a fundamental inquiry into the dynamic processes that built the outer solar system, and whether the worlds we see there are native-born or ancient refugees from a long-vanished inner realm. One of the most perplexing contradictions about Haumea emerges when we consider its history alongside our limited view of its surface. We are almost certain this world endured a collision of unimaginable violence, an impact so powerful it spun the dwarf planet into a tumbling football and blasted a whole family of smaller objects into existence. In the aftermath of such a cosmic catastrophe, you would naturally expect the surface to be a nightmarish landscape pockmarked with countless craters, the scars from eons of subsequent bombardment in the crowded Kuiper Belt. Yet the data we have, as frustratingly indirect as it is, suggests something entirely different. Haumea's surface appears to be surprisingly smooth, lacking the obvious large-scale cratering we see on other, similarly ancient bodies like Pluto's moon Charon. This creates a fascinating puzzle. Is Haumea's surface genuinely young, or are we simply unable to see the craters that must be there? The most thrilling explanation is that Haumea is a geologically active world. The apparent smoothness could be the result of constant resurfacing, a process that effectively erases the evidence of old impacts almost as quickly as they occur. We've already discussed the possibility of cryovolcanism, where a warm, slushy mixture of water and other compounds erupts from beneath the icy crust. If such activity is ongoing, these icy flows could gradually fill in and smooth over large impact basins, much like how lava flows on Earth's moon created the dark, smooth plains known as Maria. Another resurfacing mechanism could be linked to Haumea's extreme shape and rapid rotation. The incredible centrifugal force at its equator might cause the entire icy mantle to slowly circulate over geological timescales, a process known as solid-state convection. In this model, warmer ice from the interior slowly rises while colder, denser ice from the surface sinks, constantly turning the crust over like a cosmic lava lamp and erasing craters in the process. This would make Haumea far more dynamic than we ever imagined, a world that actively heals its own wounds. However, we must also confront the very real possibility that our observations are simply not sharp enough to draw a definitive conclusion. With our most powerful telescopes, Haumea remains a single, brilliant pixel of light. Everything we know about its topography is inferred from the subtle changes in its brightness as it spins. This technique is excellent for detecting large-scale variations, like the difference between a bright, icy plain and a massive, dark crater, but it is virtually blind to smaller features. A crater that is 10, 20, or even 50 miles across would be completely invisible to our current methods. It is entirely possible that Haumea's surface is in fact a rugged, cratered terrain, but that the craters are simply too small for us to detect from our vantage point over 4 billion miles away. The smoothness we infer might just be an illusion of resolution, a case of our vision being too blurry to see the true texture of this distant world. This uncertainty places Haumea at the center of a classic scientific debate. Is it an ancient, static relic whose scars we cannot see, or a surprisingly young-looking world whose face is being constantly renewed? The answer has profound implications. If the surface is genuinely smooth, it strongly supports the existence of a significant internal heat source, whether from radioactivity, tidal forces, or the remnants of its formation energy. This would make Haumea a member of an exclusive club of active icy worlds, alongside Europa and Enceladus, and would make the possibility of a subsurface ocean much more likely. If, however, the craters are there but hidden, it paints a picture of a more conventional, albeit bizarrely shaped, frozen fossil. Resolving this mystery is perhaps the single most compelling reason to send a dedicated spacecraft mission to Haumea. Only a close-up visit could map its surface in high resolution, counting the craters to determine its age and searching for the telltale signs of recent geological activity. Until then, the apparent lack of large craters remains a tantalizing clue, a silent testament to the fact that Haumea continues to guard its deepest secrets closely. The delicate ring encircling Haumea does not exist in isolation. It is a participant in a complex gravitational ballet with the dwarf planet's 2 moons, a relationship that is central to its very existence. While we often picture rings as static, beautiful halos, they are in reality dynamic and fragile structures that require some form of confinement to prevent their particles from slowly drifting apart over time. In the case of a massive planet like Saturn, this shepherding is done by small moons orbiting within the ring system itself. For Haumea, the situation is more intricate, as the primary gravitational influences come from the much larger and more distant Hioka and Namoka. Their orbits, particularly that of the inner moon Namoka, likely pass close enough to the ring's outer edge to exert a regular, periodic tug on the icy particles within it. These repeated gravitational interactions can create what are known as Lindblad resonances, where the orbital period of the ring particles synchronizes with the moon's orbit. This resonance acts as a stabilizing force, effectively defining a sharp boundary for the ring and preventing the particles from spreading inward or outward. It's a delicate balance where the moon's gravity provides just enough influence to corral the ring without destabilizing it completely, a testament to the fine-tuned mechanics at play in this miniature solar system. The possibility of unseen shepherd moons, however, remains a tantalizing and plausible explanation for the ring's precise structure. The ring's sharp edges, as revealed by occultation data, are remarkably well defined, much sharper than would be expected from the influence of the 2 known moons alone. This has led astronomers to speculate that there could be 1 or more very small, undiscovered moonlets embedded within the ring itself, too faint for our current telescopes to detect. These hypothetical moonlets would function like their counterparts around Saturn, their minuscule gravity creating gaps and sculpting the ring's edges with incredible precision. As they orbit within the ring, they would sweep clear paths, their gravitational pull kicking any stray particles back into the main band. The search for these tiny shepherds is a major goal for future observations, as their discovery would provide a neat and elegant solution to the mystery of the ring's confinement, completing our picture of the Haumean system's architecture. Yet, this entire dynamic system is further complicated by Haumea's own bizarre properties. the dwarf planet's extreme ellipsoidal shape creates a gravitational field that is anything but uniform. This lumpy gravity introduces chaotic perturbations that both the ring and the moons must contend with. A particle in the ring isn't just feeling the simple, clean pull of a spherical world. It's navigating a complex landscape of gravitational highs and lows generated by Haumea's elongated form. This uneven pull could be creating unstable zones that the ring simply cannot occupy, effectively helping to define its inner edge. Simultaneously, the gravitational tugs from Hioka and Namoka are constantly changing as their own orbits are perturbed by Haumea's shape. Namoka's chaotic path, in particular, means its influence on the ring is not perfectly regular and predictable. This creates a feedback loop of incredible complexity, where the moons shape the ring, but the ring's own mass and the primary's irregular gravity, in turn, subtly influence the long-term evolution of the moon's orbits. Modeling this three-body plus ring system is a formidable challenge in celestial mechanics, a puzzle that continues to push the limits of our computational models and our understanding of how gravity orchestrates motion on the very farthest edges of our planetary system. While the brilliant signature of water ice dominates the light bouncing off Haumea, astronomers are engaged in a far more subtle detective game, searching for the faintest whispers in its spectrum that hint at other, more exotic materials. This is our 23rd mystery, the spectral signatures of unknown substances. Analyzing a spectrum is like taking a celestial fingerprint. Every chemical compound absorbs and reflects light in a unique pattern, leaving dark and bright lines at specific wavelengths that act as a barcode identifying its presence. The challenge with Haumea is that the signal from water ice is so overwhelmingly strong that it can mask the much fainter signatures of other compounds. Unmasking these subtle clues, however, could completely reshape our understanding of the dwarf planet's chemical complexity and the conditions in the ancient Kuiper Belt. One of the most sought-after fingerprints is that of ammonia hydrate. This is a compound where ammonia molecules are locked within the crystalline structure of water ice, acting as a powerful antifreeze. Finding ammonia on Haumea would be a game-changer. Its presence would significantly lower the melting point of ice, making the existence of a subsurface liquid ocean or slushy mantle far more plausible. It would provide a ready mechanism for cryovolcanism, explaining how a salty, ammonia-rich brine could remain liquid enough to erupt onto the surface, depositing the fresh ice we observe. The search for its spectral signature is incredibly difficult, as its features are broad and lie in wavelengths where Earth's own atmosphere interferes with observations. Some studies have hinted at a possible detection, but it remains controversial, a tantalizing maybe that drives the need for more sensitive instruments. Beyond ammonia, scientists are on the lookout for the signatures of methane and nitrogen ices. These volatile compounds are common on other large Kuiper Belt objects like Pluto and Eris, often giving them their characteristic dark, red-colored patches of tholins. If Haumea possesses methane ice, even in small patches, it would provide the raw material needed for radiation to create the reddish tholin layer we suspect colors its surface. The apparent lack of a strong methane signal is in itself a curious finding. It suggests that Haumea's surface might be unusually pure in terms of water ice, or that any methane present is effectively hidden, perhaps buried beneath the surface or so thoroughly converted into tholins that the original ice is gone. Another fascinating possibility is the presence of various salts like sodium carbonate or magnesium sulfate. These would be left behind when liquid water containing dissolved minerals erupts onto the surface and the water sublimates away. Detecting salts would be a smoking gun for past or present cryovolcanic activity, direct evidence that Haumea's interior has at some point hosted liquid water in contact with a rocky seabed. The immense difficulty of this task cannot be overstated. From our vantage point, Haumea is an infinitesimally small and faint object. the light we receive is incredibly scarce, and separating it into a high-resolution spectrum is like trying to read a book by the light of a single candle that is miles away. The fingerprints of these other compounds are not bold, dark lines. They are subtle, shallow dips in an already noisy signal. Making a confident detection requires hours upon hours of observation with the world's largest telescopes, and even then, the data is often ambiguous. This is why every new observation is a major event in the small community of Haumea researchers. A slight, statistically significant dip at a specific wavelength can spark a flurry of new papers and models, as scientists debate whether they are truly seeing ammonia or just an artifact of the complex way light interacts with crystalline ice grains of different sizes. The quest to decode Haumea's full spectral barcode is a testament to the patience and precision of modern astronomy, a painstaking effort to listen to the faintest echoes of chemistry from the edge of the solar system. Now we arrive at a mystery that reaches beyond the physical nature of Haumea itself and into the very language we use to understand our solar system. This is the puzzle of its proper classification, a debate that forces astronomers to confront the limitations of our neat and tidy categories. When the International Astronomical Union created the definition of a dwarf planet in 2006, they established a key criterion known as hydrostatic equilibrium. This is a fancy term for a simple idea that an object has enough self-gravity to pull itself into a roughly spherical shape. It's this rule that separates the dwarf planets like Pluto and Eris from the countless irregularly shaped asteroids and comets. Haumea, true to form, throws a massive wrench into this system. It is clearly massive enough to be considered a dwarf planet, yet its shape is anything but round. It's a stretched, flattened ellipsoid, a tumbling cosmic potato. So the fundamental question arises, does Haumea even satisfy the requirement of hydrostatic equilibrium? And if not, what does that make it? The answer is not as straightforward as you might think, and it reveals a fascinating nuance in planetary science. The key is that hydrostatic equilibrium isn't about being a perfect sphere. It's about an object achieving a balanced shape under the influence of its own gravity. For a slowly rotating body, that balanced shape is indeed a sphere. But for a world spinning as fast as Haumea does, the balanced form is different. The immense centrifugal force generated by its 4-hour day fights against gravity, bulging the equator and flattening the poles. In a very real sense, Haumea is in hydrostatic equilibrium, just not the kind for a sedentary world. Its peculiar football shape is the direct result of it finding a new balance between the inward pull of gravity and the outward push of its rapid rotation. From this perspective, Haumea doesn't break the rules of the dwarf planet definition. It simply follows them under extreme conditions that the rule makers may not have fully anticipated. It is a dwarf planet that has been sculpted by its own incredible energy, a world in a different kind of gravitational balance. This leads to a broader, more philosophical debate about how we classify celestial bodies. Is Haumea best described as a dwarf planet, or is it more accurate to simply call it a large trans-Neptunian object? The term trans-Neptunian object, or TNO, is a broad bucket for anything orbiting the Sun beyond Neptune, from tiny icy rocks to Pluto itself. It's a geographical label, not a statement about physical characteristics. Calling Haumea a TNO is factually correct, but it feels inadequate, grouping this dynamic, complex world with inert lumps of ice and rock. The term dwarf planet, on the other hand, confers a certain status, implying a level of geological significance and complexity. By that measure, Haumea certainly qualifies. It has moons, a ring system, evidence of geological activity, and a differentiated interior, all hallmarks of a complex world, not a simple fragment. Its bizarre shape is a feature of its unique history, not a sign of insignificance. The classification struggle with Haumea is part of a larger pattern in astronomy, where new discoveries consistently challenge our existing boxes. When Ceres was found in the 19th century, it was called a planet, then demoted to an asteroid, only to be re-promoted to dwarf planet status in 2006. Pluto suffered a similar, very public reclassification. Haumea's case is perhaps even more subtle because it forces us to refine our definitions, not just reassign an object. It asks us to consider if hydrostatic equilibrium should have a speed limit, or if we need to account for rotational deformation in our official categories. This isn't just academic pedantry, it shapes how we prioritize scientific study. Labeling Haumea a dwarf planet rightly marks it as a primary target for understanding planetary formation and evolution, whereas classifying it as a mere TNO might see it lost in a crowd of thousands. The debate over its place in our solar system's family tree is a testament to its unique nature, a reminder that the universe is always more complex and wonderful than our human-made systems for describing it. Haumea refuses to fit neatly into a box, and in doing so, it challenges us to think more deeply about what makes a world a world. And so we reach the final and perhaps most profound mystery surrounding this distant world. How will we ever solve the others? For all our powerful telescopes and sophisticated computer models, Haumea remains a flickering enigma, a world whose deepest secrets are locked behind the sheer barrier of distance. The ultimate key to unlocking the 24 puzzles we've explored lies not in better observations from Earth, but in the ambitious, long-term dream of dispatching a robotic emissary on a one-way journey to the Kuiper Belt. A dedicated spacecraft mission to Haumea represents the next great leap in our exploration of the outer solar system, a venture that would transform this faint point of light into a richly detailed world with a story to tell. Envisioning what such a probe would look like is to design a machine for extreme exploration. It would likely share a family resemblance with NASA's New Horizons probe, which gave us our first breathtaking close-ups of Pluto, but with crucial upgrades tailored for Haumea's unique challenges. The journey itself is the first monumental hurdle. Even with a gravity assist from Jupiter to slingshot it outward, a spacecraft would face a travel time measured in decades, perhaps 15 to 20 years or more, requiring incredibly robust systems and a power source that can last for half a century. A radioisotope thermoelectric generator, which converts the heat from decaying plutonium into electricity, would be essential, as solar panels are utterly useless so far from the sun. Upon arrival, the mission profile could take two forms. A fast flyby would be simpler and cheaper, offering a frantic, hours-long dash past Haumea, capturing a torrent of data. But the scientific crown jewel would be an orbiter, a craft sophisticated enough to fire its engines and break into orbit around the dwarf planet, allowing for a detailed, long-term mapping campaign that could last for years. The scientific instruments on board would be a suite of exquisitely sensitive eyes and ears, each designed to answer a specific, long-standing question. A high-resolution camera would be the most dramatic, finally revealing the surface geology we can only guess at. Is it smooth or scarred with craters from the ancient impact? Are there vast cryovolcanic plains, towering mountains, or deep chasms created by its rapid spin? A thermal emission spectrometer would scan the surface for heat signatures, searching for the telltale warmth of recent geological activity and pinpointing the locations of any potential ice volcanoes. A dust analyzer would sample the ring particles directly, determining their composition and age to confirm if they are indeed remnants of the giant impact. Perhaps most critically, the spacecraft would carefully track its own orbit around Haumea. Tiny deviations in its path, caused by the subtle tugs of Haumea's uneven gravity field, would allow scientists to create a precise gravitational map. This map would be like a cosmic X-ray, revealing the hidden internal structure, the size and density of the rocky core, and crucially, whether there are pockets of less dense material that could indicate a subsurface ocean. The scientific payoff of such a mission would be nothing short of revolutionary. It would answer definitively the question of Haumea's internal heat and potential habitability. It would allow us to count the craters on its surface and finally determine its true age and geological history. By analyzing the composition of Hioka and Namoka up close, we could confirm their origin as impact fragments, essentially using them as samples of Haumea's interior without having to land. The data returned would not just solve the mysteries of one world, it would provide a foundational case study for understanding the entire population of dwarf planets. Haumea, with its rapid rotation, ring, and family of fragments, is an extreme example, a natural laboratory for testing our theories of planetary formation, collision, and evolution under conditions we cannot replicate anywhere else. The challenges of mounting this mission are immense, requiring international collaboration, sustained funding, and technological patience on a generational scale. But the potential reward is a complete rewriting of the chapter in our textbooks dedicated to the frozen frontiers of our solar system, replacing speculation with certainty and revealing the full, magnificent story of one of the strangest worlds we have ever discovered. But why should we, here on our warm, rocky world, care about the peculiarities of a distant, tumbling dwarf planet? The answer is that Haumea is far more than just a celestial oddity. It is a crucial piece in the grand puzzle of our solar system's history. Its mysteries matter because this world acts as a unique and remarkably preserved time capsule, a relic from an era of cosmic chaos that shaped everything we see today. While the inner planets like Earth and Mars have been extensively reworked by billions of years of geology, weather, and life, the frozen depths of the Kuiper Belt have remained largely unchanged. Objects like Haumea have been sitting in a deep freeze since the solar system's infancy, their essential properties locked in ice. By studying it, we are conducting a form of archaeological astronomy, digging into the frozen past to understand the violent processes that built our planetary neighborhood. The most significant clue Haumea provides is direct evidence of the colossal collisions that were once commonplace. The leading theory of our solar system's early days, often called the Late Heavy Bombardment, suggests a period of extreme violence where protoplanets smashed into each other with terrifying frequency. For the Earth, the most famous relic of this time is the Moon, believed to have formed from debris after a Mars-sized object struck our young planet. Haumea offers us another, even more extreme example of this process. Its rapid spin, its family of moonlets, and its entire clan of related objects all point to a single, world-shattering impact. But unlike the Earth-Moon system, which has been heavily modified by subsequent events, the Haumea system appears frozen in time, preserving the aftermath of that impact with stunning clarity. It gives us a clean, isolated laboratory to study the physics of these gigantic collisions, how much energy was involved, how material was ejected, and how the fragments settled into new orbits. Understanding this one event helps us model the chaotic environment of the early solar system, revealing how these violent encounters not only built worlds but also determined their final spins, shapes, and compositions. Furthermore, Haumea's very existence challenges and refines our fundamental models of planetary science. Its bizarre properties force us to ask if our physical laws, developed by observing the relatively sedate planets of the inner solar system, fully apply in the extreme conditions of the outer darkness. For instance, the fact that it maintains a stable ring system defies our previous understanding that such delicate structures could only survive around massive planets. This forces astronomers to develop new models that account for how rings can form and persist around small, rapidly rotating bodies. Similarly, the presence of fresh, crystalline ice on its surface pushes the boundaries of our knowledge about internal heat and geological activity. It suggests that even small, distant worlds can harbor unexpected sources of energy, whether from tidal forces, radioactivity, or the remnants of their formation. Each time Haumea contradicts our expectations, it doesn't just create a new mystery. It pushes the entire field of planetary science forward, compelling us to create more robust, flexible, and accurate theories that can account for the full diversity of worlds in our cosmos. Ultimately, the greatest importance of Haumea may lie in what it tells us about our own place in the universe. For centuries, we viewed the solar system as a neat and orderly place with a few familiar planets. The discovery of the Kuiper Belt and objects like Haumea revealed a vast, messy, and dynamic frontier that is still evolving. Haumea teaches us that our solar system is not a static museum exhibit but a living, breathing system with a complex and violent history. Its story of planetary migration, colossal impacts, and hidden activity suggests that the processes that formed Earth and the other planets were not unique or special, but part of a universal narrative of creation and destruction. By unraveling the secrets of this distant, football-shaped world, we are not just learning about Haumea, we are piecing together the origin story of our entire cosmic home, gaining a deeper appreciation for the dynamic and often violent forces that crafted the worlds, including our own, and set them spinning in the great void. And so, after this journey through 25 of the most profound enigmas, what are we to make of Haumea? It is a world that defies simple description, a celestial maverick that challenges our very definitions. From its frantic, football-like spin and the chaotic dance of its moons to its inexplicable ring, and the youthful, crystalline ice that glosses its surface, every aspect of this dwarf planet seems designed to perplex. We've explored the violent impact that may have given it birth, the high density that hints at a rocky core from a warmer birthplace, the faint blush of complex organics on its surface, and the tantalizing possibility of a hidden subsurface ocean. We've grappled with its extreme axial tilt, the long-term stability of its rotation, and the frustrating challenge of simply measuring its true size from across the solar system. Each mystery, when examined alone, is a head-scratcher, but when viewed together, they intertwine to form a single, coherent narrative of a dynamic and complex history. The spin explains the shape influences the moon's orbits, the moons may provide the tidal heat for geological activity, and that activity renews the surface ice, which in turn affects its color and reflectivity. Haumea is not a collection of random oddities. It is an intricate system where every puzzle piece is locked into the next, a perfect demonstration of how one cataclysmic event in the solar system's youth can echo through billions of years, creating a world of breathtaking uniqueness. Haumea's greatest lesson may be that our solar system is far from a settled, orderly place. It is a dynamic and ever-changing arena where the rules of physics can produce outcomes more wonderful and bizarre than we ever imagined. This distant, tumbling world forces us to look past the familiar planets and recognize that the real action, the stories of creation, destruction, and potential rebirth, are unfolding in the frozen darkness of the Kuiper Belt. It stands as a testament to the violence of our past and the hidden activity that may still be present in the most remote corners of our cosmic backyard. Now we turn the question over to you. After exploring these 25 unexplained mysteries, which one captures your imagination the most? Is it the possibility of a hidden ocean deep within its core, a secret environment that could challenge our understanding of where life might exist? Or is it the dramatic story of its birth, a colossal impact that set it spinning and created its entire family of moons and fragments? Perhaps the delicate, impossible ring system around such a small world is the detail that you find most compelling. We want to hear your thoughts. Share which mystery fascinates you the most in the comments below, and let's continue the conversation. The story of Haumea is far from over. With every new observation and every future mission proposal, we will learn more. So stay curious, keep looking up, and remember that the universe is always ready to surprise us with wonders beyond our